So let's look at chapter 4. Yep. Types of chemical reactions and solution stoichiometry. When we talk about solutions, I mean, we've already covered that topic. A solution is a homogeneous mixture, but a great many chemical reactions occur in solution. When you go far enough afield, you can get all kinds of solutions, solvents for your chemical reactions, but we're going to stick with primarily water as the solvent. So this characterizes water as a polar solvent. Now, I know we haven't gone into that kind of much detail with polarity yet, but all that means is for any molecule to be polar, it has to have an uneven distribution of electron density, which means it's slightly polar on one end, slightly positive on one end, slightly negative on the other. And that's what's they're trying to show you there with this water molecule. It's bent, 2 hydrogens, 1 oxygen, and each one of the bonds tends to be polar toward the oxygen. That just means that oxygen has a stronger pull on the electrons. This is a shared pair of electrons here, but they spend more of their time on this end than on that end. That's the short version. Then when you look at the overall molecule, it has a slight positive end this side and a slight negative end this side. So that what that does is when we try to put something into solution, if the solute also is polar, then it will align itself so that its positive end is facing the water's negative end, and that those molecules will also associate their negatives to the positives, and that makes them more soluble. Oops, got a little short video. I think this one's narrated. It must be Canadian because that English and French. This is what it would look like for a cube of sodium chloride to encounter water molecules. So you're salting your water before you boil your pasta, and that goes into solution because sodium and sodium chloride is a collection of cations and anions. And notice that the positive end attacks the negative, the anions, which are the blue ones, and the negative end attacks the sodium ions. And then when they're in solution, they're hydrated. That is, they're surrounded by as many water molecules as can accommodate themselves around the ions. And that keeps them in solution, because if you have a sodium ion in solution and you have this part of the molecule like that, or over here, like this, this negative side is associated all around it, but you still got these positives sticking out over here, like that. And they're going to associate with other water molecules. Yeah. So you still have those bonds formed, and the strength of the pull of these other water molecules around the ones that are closest to the cation, in this case, tend to pull it. And they provide enough energy to dislodge that ion from the crystal and keep it in solution. All right, come on. I need to go to the next slide here. There we go. Now, I use terminology that I hadn't defined yet, and that's not fair. So let's define our terms. The solvent is the major component in a solution. And there can only be one. Only one solvent in a solution description. The solute can be many, and they are the minor components. In terms of numbers of particles. So you can have an aqueous solution and you can put sugar into it, you can put salt into it, and put vinegar into it, goes into solution. Those are all solutes in the water as our solvent. Now, when we talk about electrolytes are, it's simply a name for anything that will dissolve in water and conduct electricity. So just because it dissolves in water doesn't mean it's electrolyte. What we're usually saying is that the electrolyte breaks apart into separate ions, because for current to flow through any conductor, you need mobile charges. If you've got a copper wire, the mobile charge is an electron. If you've got Allison. Let's see if I don't want to miss anybody. Let me check to be sure. Intro. So that's what we mean by electrolyte. The electrolyte in solution will conduct electricity. It will support a current through water. Pure water is an insulator. At relatively low voltages, water will not conduct electricity. Now, if you get the voltage high enough, of course, then you've got enough energy in there to ionize water, and then it'll conduct. So that's why they say in a lightning storm, don't stand in a puddle of water, because there's enough voltage in that lightning strike to ionize the water, and you're like a good lightning rod. In fact, there was a girl, I didn't know her, we weren't that close, but she was in my high school class, and I was a teacher's kid in a private school. That's the only reason I was there, because we could get a break on the tuition. But most of these kids were rich, and their parents had separate houses all over the place. And this one girl had her parents had a cabin in North Georgia. I lived in Atlanta at the time. And she went up there to spend the weekend, and she was in the tub when a lightning storm rolled through. Well, she was also on the telephone talking to friends. Well, as luck would have it, lightning struck the telephone line, went through the line, through her, through the tub, into the ground. And we had to scratch her name from the roster. So, electrolyte is anything that makes water conductive. So, for instance, something that doesn't make water conductive but is soluble is table sugar. You can put a lot of table sugar in a solution, but it'll never conduct electricity because there are no mobile charges. Okay. Let's see. We also differentiate strong electrolytes and weak electrolytes. When I say something dissociates into charges, something that completely dissociates into positive and negative charges in solution would be like sodium chloride. So you have all these sodium ions and all these chloride ions in aqueous solution that will conduct electricity very efficiently. And if you put say a light bulb in the circuit and dip the electrodes into this solution, the light bulb will be as bright as it can be on that voltage. But if you have a weak electrolyte, something that does not dissociate to a great extent, like for instance, a weak acid, like acetic acid, vinegar. Then you dip your electrodes in there. It'll conduct electricity, but not very efficiently because you don't get this broken into ions. Just a very few of these come from that. And that's not enough to make the light bulb very bright. So those are weak electrolytes. Or even some types of ionic compounds are weakly dissociating in water. Will give you a similar effect. Non-electrolytes are like table sugar. Right? They don't conduct electricity at all. I have to start this one.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
There we go. Okay, now we're going to keep myself on track here. Yeah. Chemical reactions that solutions can undergo. First of all, we need to know something about the reaction itself. Right? These compounds or elements may be in solution, but what components of that solution actually participate in the reaction? Very often, the solvent itself is a participant, right? And we'll encounter that in more detail when we get to acids and bases. But we also need to know not just who participates in the reaction, but the amounts of each one of these reactants that are present in the solution. So we know that solutions can be, or these mixtures can vary in concentration. That is, you can have a lot of salt in the solution or just a little bit of salt, for instance. And that will have a bearing upon the reaction as it proceeds, whether it even happens or whether it happens slowly or fast. And we'll talk more about that in the next chapter, I think. Chapter 5. No, we're going to get gases first. I'm sorry. I'm mixing up 102 with 101. 102, we're getting ready to do kinetics, which is reaction rates. So if you come back for the second semester, we'll talk about reaction rates. But we need to know what type of reaction it is and the participants, and we need to know amounts, how much of each one there is. And there are different ways to express these concentrations. The most useful one for the chemical reactions is molarity. Molarity is simply a definition of concentration, which means moles of whatever the compound is per unit volume, which is, in this case, liters. And it has to be moles, it has to be liters to be molarity. So if we know how many moles are in a certain volume, we can calculate the molarity. But this is like any mathematical equation. It's got three variables in it, right? So if you know two of them, you can solve for the third one. If we know the molarity and we know the volume we want, that tells us how many moles we got. We'll be using that arrangement also. So instead of, that's my abbreviation, that's N for moles. Notice it doesn't have a zero up there in the right-hand corner, so it's not neutrons. It's moles, and this is volume. So if we solve it now and we want to find out number of moles, we have the molarity times the volume, as long as the volume is in liters. Okay, so say we have 500 grams of potassium phosphate and dissolve it in a 1.5 liters of solution. What's the molarity? Well, we know we need to calculate the molarity, and we've got the correct volume, 1.5 liters. That's the correct units, but we don't have moles. We've only got grams. So what we have to do is go back to our nomenclature study. We've learned how to name compounds, and we write the formula, potassium phosphate, right? Phosphate, PO4, and it has a 3- charge, so this has to be 3, because potassium is an alkali metal and it's a +1 charge always. So there's your formula. That's why I insisted so heavily that you learn the symbols, learn how to write the compounds, because we're going to be using them just over and over again. And if you don't know that, you can't calculate the molar mass. So potassium is 39.10 to 2 decimal points. So we want 3 of those. We want phosphorus, which is 3097, just 1 of those, and 4 times 16, which is 64 for oxygen. And we just add those together, and that gives us our molar mass, so that we can convert 500 grams of potassium phosphate into moles. Otherwise, we can't solve the problem. 39.1 times 3, and 30.97, and 64. So 212.27. So we have 150, no, 500, excuse me, 500 grams. And we want to convert that to moles. So we need grams on the bottom, moles on the top. Well, grams happens to be 212.27. That. Divide that into 500. And we get 2.355 moles of potassium phosphate. Now we can calculate molarity. And 1.5 liters. And I get 1.57 molar. It's coming up here. Okay. Now, why do we need to know this? Because when we try to conduct a reaction with something like potassium phosphate, some other chemical, we need to know how much, right? Last chapter 3, we talked about mass, just straight mass converting to moles. But if we're going to use solutions, we need another way to determine the number of moles of each reactant. And if they're in solution, we start from here and we use molarity times volume. If we know the volume of a certain molarity, now we can calculate moles. So when we've got the balanced equation and we're trying to do stoichiometry, you always have to aim for moles to get anywhere in that equation. And this is one of the ways. Okay. So we've got electrolytes to deal with also. So if our reactant is molecular and it's not dissociating, then once you find the concentration, then you're good to go. But if the reaction is between this ion and that ion, and you put this ion in solution with a counter ion of some kind, and the other one with another counter ion, what you need to know is the concentration of the reactant ions. Okay, so if we have, in this case, 0.25 molar calcium chloride, what's the molarity of the calcium? Well, it's the same as the whole, because there's only one, there's a 1-to-1 ratio. Calcium chloride, there's 1 calcium for every mole of calcium chloride. So if you have 0.25 molar calcium chloride, you also have 0.25 molar calcium ions once it's in solution. But with the chloride, for every 1 mole of the molecule or the formula, you've got 2 moles of chloride. So if the actual concentration of the formula is 0.25 molar calcium chloride, then you have 0.5 molar of chloride in solution. Okay. Now that used to be a real issue for medical students, because long time ago, I think, they had to, the nurses usually, or the lab techs, whoever was designated, had to prepare solutions for patients, you know, and you wanted them to be isotonic, right? So that they wouldn't, you pump them into your patient and kill them by rupturing their blood cells, for instance. So you would have to know the proper molarity of all the components in the solution, so that you could match the osmotic strength of their blood tissue, their tissues, the solutions in their tissues. So if you calculated based upon the molecule and you put that in there, then you're going to have 3 times as much concentration of the ions, because you've got the 0.25 calcium and 0.5 chloride. You're going to have 0.75 molar ions in solution, and you wouldn't rupture their cells. I guess you'd crenate their cells. They just go like that if the solution you put into them is too concentrated. So it was important to know this stuff and know how to make solutions like that. Now we've eliminated that problem by just preparing the solutions in sterile bags, and you just pull one off out of the cooler and hook it up to your patient, and you know, liability is not a problem. Unless somebody at the company that made the bag pulled a boner, and then you're killing patients right and left, but you're not liable anymore. The patient's still dead. Okay. And when we made our own solutions, that's back when you had to use glass bottles, and you had to put them in the autoclave and sterilize them. Okay, which of the following solutions contains the greatest number of ions? All right, for this situation, we have number of moles equals molarity times volume. Okay, so if we want to know which one has the greatest number of ions, numbers means moles. Right? We don't have to go all the way to use Avogadro's number. Just if we're comparing numbers, we can use moles because that's a counting unit. So if we bring Henry Ford out of mothballs and use our assembly line, let's see, only do one of those. Yeah. Okay. And then 200 and 800. 200 and 800. This is milliliters for each one. And notice I didn't change them to liters. And I'm going to explain that in just a minute. So we've got 0.1 molar of each compound. So this tells us the moles of each formula unit. But I guess I better explain it. If you multiply molarity times milliliters, you get a unit called millimoles instead of molar. You get millimoles. So in this case, I'd have 40 millimoles of that compound. Now, just to prove that millimoles works, if we have moles, if molarity equals moles there, if I use, instead of moles and liters, I use millimoles and milliliters, right, which is what I would do here, then I could go backwards. I could say I've got 40 millimoles divided by 400 milliliters. Okay. Remember, when you do calculations, you do the same thing to the units as you do to the numbers. So if I divide this one into this one, I can divide millimoles by, I should put that. That looks like millimeters. Millimoles divided by milliliters. Well, the milli cancels out, and you got moles divided by liters. So you end up with the same number. And it saves you a lot of, we could call this 0.4 liters, 0.3, 0.2, 0.8, and we get moles out there. If you want to do that, that's fine. In this case, I would have 30. In this case, I'd have 20. In this case, I'd have 80. Now, this is millimoles of the compounds. Right? But I want to know how many ions. So if these are the compounds, then I need a factor, a conversion factor that will get rid of compound and leave me with ion. Okay. So what's the ratio? Well, for every 1 millimole of compound, how many ions do I have in sodium chloride? I have 2, right? 1 sodium and 1 chloride. Calcium chloride, I have 3 ions per 1 compound. Third one is iron 3 chloride. So that's 1 iron and 3 chlorides is 4 ions for 1. And the last one is sucrose. It doesn't have any ions, so throw it out. Okay, so if we multiply these and we're just comparing which one has the greatest, then I could just say 2 times 4 is 80, and 3 times 30 is 90, and 4 times that's 80. So the greatest number is the second one, calcium chloride. Okay. Okay, we talked about this before, didn't we? Right, if you're going to solve a problem, you got to ask the question. Find out what the question is. Then how do you get there? Sometimes you can get there very simple, one-step solution. Sometimes you have to break it into individual pieces, make it simple, and then bring the answers of those pieces back together. So this just drives home the point. Just because you have more volume doesn't mean that you have more ions. All right. Now, when I was working in a service lab, actually I was running it. So I had one assistant, and we would serve the needs of up to 15 research scientists. They would submit samples, soil samples, plant samples, for analysis. And the soil samples, we have extractants that would pull out of the soil various nutrients, usually inorganic nutrients. And then we run them through various procedures to analyze how much of each one there was in the extractant. Well, these extractants are usually fairly dilute in their concentrations. So we had to run hundreds of them a day. So it'd be difficult. We'd have to start really early. You know, we just pretend we were donut people. We'd have to start really early if we were going to make up that much solution at those low concentrations for each run each day. It's more efficient to make up the correct ratio of all the components of the solution at higher concentration and keep them in stored. And then when we needed the diluted solution, we take some of those out of there and dilute them with more solvent. The ratios would still be the same, but the concentration would be decreased because we're increasing the concentration of, we're increasing the amount of the solvent. And that's what this exercise is trying to show. If we have the molarity of it's M1V1, M2V2, so it could go either way. But for argument's sake, let's say this is the concentrated molarity. But we're going to take a certain volume out of that concentrated molarity, and we're going to bring it to this new volume by adding more solvent. And that's supposed to give us this diluted concentration. So there's your formula. Now, why does it work? Let's see, do I have a slide on that? Yeah, why does this thing work? Well, actually pictures help us a lot here. If we have a container of our solution and it's at that high concentration, and then we've got a volumetric container of some kind, and say it's a volumetric flask. And that line says, if we fill it with water to that point, we know it has exactly that volume in it. So let's just keep it simple. Say it's 1 liter. And we want this diluted concentration over here. And the volume we know is 1 liter. Okay. So if we know the concentration here, we can pull part of this out of there and dilute it with extra solvent. So we're going to pull out this volume of the concentrated one. How many moles did we pull out of that here? Well, the number of moles we pulled out is equal to the number of moles from the concentrated side is equal to the concentrated molarity times the volume that we pulled out. That's the number of moles. Now, as we transferred it over there, supposedly we didn't spill any, right? So we have the same number of moles going in here as we had over there. So over here, we have the same number of moles on the diluted side is equal to the moles we pulled out. Well, what is this one equal to? This one's equal to that one. So we're saying that the moles that we pulled out concentrated equals the moles that we put in the dilute. That means these two can be equal. And now we have a formula. All we need to know is 3 of those and we can calculate the 4th one. Okay. And that's what this slide is trying to show. Those 2 moles are exactly equal. And that's why we can say that M1V1 equals M2V2. Okay. I'm gonna skip this slide. All this slide says is, what do you do to make your solution more concentrated? What do you do to make it less concentrated? More concentrated, you can't just take some out and throw it down the drain. That doesn't make it more concentrated because you've pulled out an aliquot of the same concentration and the concentration is left behind. It's the same. But if you sit it on your bench and let it evaporate, right, and your solute is not volatile, then the water evaporates and you get more concentrated. Or if you want to dilute it, you just add more solvent. That's all that slide's trying to show. Let's see, what's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? So I'm going to erase this part and leave the formula there because that's the formula we're using. Let's just take this out of the picture. And when you have problems like this, it helps to extract information so that when you try to use a formula, you put your numbers in the right place. If you try to take it from the paper directly into your formula, you may put them in the wrong place, and then obviously you get the wrong answer. So we've got MC, concentrated, concentrated, dilute, dilute. So we see which one goes where. What's the minimum volume of 2 molar sodium hydroxide? And we're going to 0.8 molar. So the concentrated one is 2 molar. And the dilute one is 0.8 molar. And our final volume is 150.0 milliliters. There's our unknown. So now we can solve our equation for the unknown. Okay, that'll tell us the volume of the concentrated one we need to dilute to this volume to give us the desired concentration. If we plug our values in, this is 2 molar. And this is 150 milliliters. Notice I didn't change the units either. And then the excuse me, that's the diluted one, right? I put the wrong one on top. Diluted 0.8 molar, and the bottom one is 2 molar. There we go. I got everything in the right place now. Notice if we keep the units the way they are, this is a ratio. So these molar units cancel, and our answer is actually in milliliters. Okay, we can only do that because this is a ratio. When we're doing the calculation of molarity using the formula, it has to be in moles and liters, or millimoles and milliliters. So if we do that calculation, let's see, maybe they'll help me out. Here we go. And solve 60 milliliters. So what that means is I need to pull out 60 milliliters of this concentrated solution and dilute it by adding more solvent until I reach 150 milliliters. Then I know I will have that concentration. Okay, now we can talk about types of reactions. These are, I guess you could call it operationally defined. What do we observe to define these reactions? Major types of reactions. Well, most reactions will fall in these 3 categories: either precipitation reaction, acid-base reaction, or oxidation reduction. I have to define my terms, of course, and that's coming. But these descriptions, these descriptive terms, we can have multiples for the same reaction. In other words, a precipitation reaction could also be a double displacement or double replacement reaction. Okay. Combination, well, let's see. It could be a combination reaction, which is often called a synthesis. Be a decomposition, which is the other way around. You take the synthesis and flip it around, you got a decomposition. Single displacement, double displacement, or combustion. So let's go to the individual slides and talk about these. A precipitation reaction is actually a double displacement reaction. What do we mean by that? Well, let's say we have a compound with a cation and an anion. in solution. Okay, this is our positive ion, that's our negative ion. And we combine it with another solution that has a cation and an anion in it. And these are both already soluble. So you put those solutions together, and then if something happens, if you get a reaction, the double displacement comes from the cation in this one substitutes for the cation in that one. So that means we would have this X over here, XB, and this would be AY. That's a replacement or a double displacement reaction. Now, depending on the nature of this association between this new cation and anion, new cation and anion, it may be soluble and it may not be. Right? Let's just for argument's sake say that this one's not soluble. So it makes a solid, and you'll see it drop out of solution. And say this one is soluble. Okay. So that describes a precipitation reaction and a double displacement reaction. Precipitate is the term we use for the solid that forms when we combine the two solutions. Here's an example. This one has several polyatomic ions in it. Barium and potassium are the cations, like barium and potassium, and this would be the nitrate, and this would be the chromate. So when we swap places, right, we get the barium combining, the potassium combining with the nitrate, and it's completely soluble. But the barium and the chromate together makes a solid that's not soluble. And that's why you see that yellow stuff in the bottom. That's barium chromate. That's a precipitate. Now, how do we know what's going to happen? Well, I've got a chart. Let's see, is it on? Maybe I'm jumping ahead of myself. Yeah, it's several slides long. I'll get to it. I got a little video here. There's some narration. No narration? I guess not. When you add sodium chloride and silver nitrate, you get silver and chloride combining, makes a solid. And you got sodium nitrate, which is still soluble. Okay, that's what we saw, that cloudy stuff. That's silver chloride. It's not soluble. Now, while we're here, what's actually going on here in solution? Before we put these things together, if this is soluble, it's actually sodium ions and chloride ions, right? In aqueous solution. And this one is silver ions and nitrate ions in solution. Right? So they're all floating around there together when we pour them together. And that means they have access to each other. Sodium now can interact with the chlorides, and that's where you get the solid form. But what's left over? Well, you still have the sodium ions and the nitrate ions free floating. Like, there's no combination there. So what drives the reaction is the formation of the precipitate. Because as we form that solid, it drops out of solution. It's no longer available. So as it drops out of solution, it's like a big, let's see, it's like a slinky. When you put a slinky on the stairs and you get it started, it goes over like that, and it pulls the rest of it with it. That's an analogy for what's happening here. The formation of that solid drives the reaction. Yeah, we've got another one right behind it. There you go. I just put this one in here because it was pretty. In this case, the solid is silver thiosulfate, which decomposes into silver sulfide. It's this one. Barium sulfate is insoluble. Those really bold one, that's the solid. And they don't have to be white, right? They can be different colors, like this silver chromate. That's a pretty complex one there, but it's pretty. All right. So let's go to the next. Go. All right. When we talk about soluble versus insoluble, at this point in the course, we'll make a distinction. When we say soluble, we actually mean it all goes into solution. When we say insoluble, we have to qualify that. It's not that everything doesn't go into solution. It's just that it's so small, it's insignificant. So as a practical matter, if you're doing bench chemistry where you want to separate cations in a mixture of cations, and you have a particular anion that you can add, and it will react with 2 or 3 cations and form a precipitate, then you can bring those out of solution, filter them out, and you've got a partial purity. But some of those cations are still in solution because it was only slightly soluble. We're calling it insoluble as a practical matter. But the reality is that insoluble can also mean slightly soluble at this point. Right? Eventually, let's see. Next semester, we learn how to actually calculate how much is left in solution. But for now, soluble, insoluble is where we're at. Now, these are the solubility rules. If you were chemistry majors, you'd memorize those. But since you're not, I give you a chart. But the chart is based upon these rules. And their rules are in order from top to bottom. If you say you've got a nitrate is formed from your reaction, it's going to be soluble every time. Nitrates, all of them are soluble. That's why we use silver nitrate to get that silver in solution, because we know all nitrates are soluble. Most alkali metals and ammonium compounds are soluble. Most chlorides, bromides, and iodides are soluble, except for silver, lead, and mercury 1. Notice how that's written. Mercury 2+. If there are 2 of them with a 2+ charge, each one is a +1 charge, right? But that's the way mercury is. It always forms a 2+ charge. It's either 2 mercuries together or it's 1 mercury. So this one is a +2 charge, and each one of these is a +1 charge. That's just the way mercury is. But when you combine it with any of these chloride, bromide, iodide, it drops out of solution. Most sulfate salts are soluble, except for barium, lead, mercury, and calcium. Those are insoluble. So you start getting more exceptions. And they're put in this order because if you look at your reaction and you've got 2 rules that are in conflict, the one above takes precedence. All right, I'm not going to go through all these because you're not chemistry majors, so you don't have to memorize them. But there is a chart. And where is that chart? I thought, there it is. It's further down the line. This chart should be, you should find it in your useful information at the back of this. If I didn't give you a second, there should be one here. Yeah, the back of this. So to use that chart, you do it like your, I don't know, they don't do that anymore. Used to have paper road atlases that you get at the filling station, and you just open them up and you'd be driving down the road with this atlas in front of your face and ram into the back of somebody ahead of you. So used to be that you could say on those road atlases, you could say, I'm starting from here, and on the x-axis and on the y-axis would be your destination. And you just go to where they meet and it'd tell you how many miles. Well, think of it in those terms. The top row here is all the cations, and the down the left-hand side are the anions. So you just follow them across until they meet. And if it's clear, it's soluble. If it's grayed out, then it's insoluble. Okay. And if you do it enough, you learn some of the rules anyway. All right, let me go back to where I left off. So which of the following ions form compounds with lead that are generally soluble in water? And nitrates are always soluble. So that'd be my guess. And sodium's in there as a ringer, right? Sodium and lead don't form compound. They're both cations. That was a trick. Okay. We started off with this discussion by writing what we call a molecular equation or a formula. Actually, a formula equation is the accurate term, because these are not molecular compounds. Molecular compounds are covalent bound, like water, carbon dioxide, so forth. These are formula equations. So, and we do them for convenience, right? Silver nitrate, sodium chloride, silver chloride solid, and sodium nitrate still in solution. And those are easier to balance when you write them that way. But once you've got them balanced, then they can be broken apart into the reality, like I did before, into the ions. And that's known as the complete ionic equation, right? That's actually what's in solution. But remember, in this case, the sodium and the nitrate don't participate. So they're just kind of sitting around there. I mean, they do contribute to the ionic structure of the solution, but as far as the reaction goes, they're non-participants. They're spectators. So if we remove the spectators from both sides, we get the ionic equation, the net ionic equation. That's silver ions plus chloride ions yields silver chloride solid. Now, the advantage to that is it removes a lot of the clutter. And as a practical matter, if you go into the lab and you want to form silver chloride as a solid, and you don't have sodium chloride, use potassium chloride, because potassium nitrate's also soluble. They're spectators. So you still got silver and chloride ions. Either one works. Here's an example where we have cobalt 1 chloride, sodium hydroxide makes cobalt 2 hydroxide, excuse me. Cobalt 2 chloride, cobalt 2 hydroxide, and sodium chloride. And the cobalt hydroxide is the precipitate. And then you segregate it out into separate ions. And notice that this cobalt 2 chloride in the formula equation is actually cobalt 2 plus and 2 chlorides because of the subscript. The chloride is the -1 charge, but you need 2 of them. So the subscript comes out to the coefficient position. And that way you lay out your complete ionic equation, then you look for the spectators, cross them out. And you end up with cobalt hydroxide yields cobalt hydroxide. Okay, this is where I would pause if we could. But since I've only got 15 minutes and it's going to take me another probably 45 minutes to finish. So if you have to go, you won't hurt my feelings. Let's see, rather than run through these, we're going to do an example. I think it'd be better. Let's do this one. So we're told that we have 10 milliliters of 0.3 molar sodium phosphate solution in one beaker, and we have 20 milliliters of 0.2 molar lead 2 nitrate in another one. And for the reaction to proceed, we dump them together. Okay. So first thing to do is to write out the formulas. Sodium phosphate. So let's put it up here. Sodium. And then we have phosphate, which is a polyatomic ion with a 3- charge. That's an alkali metal. So we need 3 of these, don't we, to balance the charges. Okay. That's an aqueous solution. And we're going to combine that with lead 2 nitrate. So we have lead with a 2+ charge, nitrate with a 1- charge. So we need 2 of these. And that's an aqueous solution. Okay. So I don't need the charges now that I've got the correct formulas. There we go. Okay, this is one of those reactions I may have mentioned. Double displacement. We can determine the outcome. All we have to do is swap partners. So sodium combines with nitrate. 1+, 1-, that's it. And we look up, well, of course, we know that all nitrates are soluble, but you can look it up in the chart if you want. So this is still soluble. If we combine lead, and lead still has a 2+ charge with phosphate, okay, and we look that up, we find that it's insoluble. So that means this is a solid. So how do we balance a 2+ with a 3-? We bring 3 over here and the 2 over there, like that. So now we have our unbalanced equation written. What precipitate will form? Well, obviously, lead 2 phosphate. That answers that question. Come on. All right, those are the ions in solution. There's our precipitate that forms. Now, the other question was, excuse me, I didn't write everything up there yet. We have to balance the equation first, and then we can put the rest of the information in there. The nice thing about these double displacement reactions, most of the time, they're easy to balance. Sometimes you don't even have to do a budget. We can do a budget, and we probably should, right? Because you're newbies at this. And I'm just going to write I'm not going to put any charges in there because we're just keeping track of things. There are 3 sodiums here, 1 phosphate, 1 lead, and 2 nitrates. Notice, since these remain intact for the reaction, I can use them as balancing units. That's one of the tricks. On this side, we have 1 sodium. We have 2 phosphate. We have how many leads? 3. And we have nitrate, 1 nitrate. Now we use our coefficients to balance this thing. We can start just about anywhere, actually. I'm tempted to start with the sodium, but let's start someplace else and see if it still works. Let's do the lead. We've got 3 leads on that side. Let's say I want 3 leads on this side. That means now I have 6 nitrates, right? 2 times 3. Well, if I get 6 nitrates on this side, I need a 6 there, right? But that also gives me 6 sodiums. Okay. Well, let's see. These are good, these are good. If I balance the sodium on this side to get 6, I need 2 here, right? 2 times 3 is 6. And that gives me 2 phosphates. We're balanced. Okay. So now that we have a balanced equation, I can remove all this and put in the other information that we're given in the problem. Because we're not done yet. You have to have a balanced equation or you can't move. 10 milliliters of 0.3 molar sodium phosphate. 10 milliliters of 0.3 molar of that compound. This one is 20 milliliters. Oops, too many. Of 0.2, 0.2 molar. That's where we're starting. What mass of precipitate will form? I don't know if you remember, but last time I said, if you're given exact amounts of both reactants, one of them is going to run out. So now we have to find out which one is limiting. Okay. In order to go anywhere in this equation, we got to find moles. So remember, if this is true, and we want to find moles, then N equals M times V. Molarity times volume will give us the moles. In this case, we're multiplying molarity times milliliters, so we're going to get millimoles. Okay, 0.3 times that is what? Well, 10 times this one is 3.00 millimoles. Is that right? 10 times 0.3. And 0.2 times 20 should be 4, correct? Tenth of that would be 2, and 2 times that would be 4. Okay, so we're good. That's how much of each one of these we've got. Okay, now that we know how much we're starting with, we can use our coefficients to tell us how much of the precipitate we're going to get with each one. If we say all of this is converted to lead to phosphate, right? If this is the nitrate, and we want the ratio of this one to that one, that's 1, and this is 3, right? So 3 into 4, right? That cancels. 3 into 4 is what? 4 thirds, and this is millimoles. So that'd be 1.33, right? That's millimoles of this compound. That's what we would get if all of this is converted into that. Now what we would get if all of this was converted into that. Now we need a ratio that gets rid of this one and gives us this one. What's the ratio? 2 of these to every one of those, right? So 2 into 3 is 1.50 millimoles of phosphate. Okay. Now, which one's limiting? The one that makes the least amount of product. This one. That's the one that runs out. Now we know we have this many moles of lead 2-phosphate. We can calculate the mass. We know the moles. So 1.33, actually, this is millimoles, excuse me. So how do we convert? Because when we calculate molar mass, it's going to be in grams per mole. So we need moles here. We had millimoles. How do we make that into moles? Well, if this is millimoles, what's this milli equal? 10 to the minus 3, right? So 1.33 times 10 to the minus 3 is the milli part, and we still have the moles out here. Okay, so that's your moles. Did I lose anybody? Because now we're going to convert moles on the bottom, grams on the top. We just need the molar mass of lead 2 phosphate. All right, so lead is here, 207.21 grams per mole, but we got 3 of them, don't we? And we got 2 phosphorus, right? Because it's 2 phosphates, that means 2 phosphorus, 3097. And then we have how many oxygens? 8. 8 times 16. That's the molar mass of that compound. It's a big one. 207.21 times 3. Okay, and then 30.97 times 2, add those together, and then 16 times 8, add those together. So I get 811.57 grams per mole. 811.57. So the moles cancel, and all I have to do now is multiply this times 1.33 with an exponent of minus 3. And I get 1.08 rounded off grams. Okay. Let's see. It's okay. That's where we started with sodium phosphate. Right, with the 3. Checking myself to see if I made it in boo-boos. That one's good. Okay. Now we find the limiting reactant, 1.5 versus 1.33. Okay, 1.33 is our limiting. So we take that and convert it to 1.08 grams. Okay. I guess you'd call that a multi-step problem. So you have to get, it's not something you can do just like this in your head. At least I've never met anybody that could do it. But there are steps that you need to follow, logical steps. Let's see, we still got this same problem. Okay, another question. What's the concentration of nitrate ions? Okay, nitrate. Where are they? Here they are. So if this is how many millimoles of the lead 2 nitrate there is, how many millimoles of nitrate? This is millimoles of the whole compound. Now, some students make a mistake and they say, okay, I need to look at that coefficient, but you don't. Coefficient is only for balancing the equation. When we're talking about absolute amounts, 4 millimoles of this compound means 2 times that, or 8 millimoles of nitrate ions. And since they did not participate in the precipitation, they're still in solution. So what's the difference? Volume. The volume change. It went from 20 milliliters to 30 milliliters, 20 plus 10. Okay. Remember, if you divide millimoles by milliliters, you get molarity because the millis cancel. So 8 divided by 30 is 0.27 molar nitrate. Okay, that's what that box tells you at the bottom. This one is a little more tricky. What's the concentration of phosphate ions left in solution? Well, let's see. Are there phosphate ions left in solution? Well, if this is the limiting reactant, then this is excess. Right? We determined that this one is limiting. That means this is excess. So yeah, there are some phosphates left over that weren't used. So what we have to do is say, all right, how much phosphate did we start with? Well, if we have 3 millimolar of this compound and it's 1 to 1, for every 1 unit here, you got one of those, then you actually have 3 millimoles of phosphate to start. Now, how much was used? Well, we know what this precipitate is, right? This one, 1.33 millimoles of this compound. So how many millimoles of phosphate? Well, the ratio is 2 to 1. So for every one of these, we get 2 phosphates. That means 2.66. 2.66 millimoles of phosphate were used. Okay. So that means what we have left over is 4 and 3, 0.34 millimoles. Right? Of phosphate. Now we can put them in the concentration. 0.34 millimoles of phosphate was unused. And the volume is still 30 milliliters. So let's see, 0.34 divided by 30 is 1.13 times 10 to the minus 2 molar phosphate. Oh, they standard notation. Okay. Just move the decimal to the left 2 places. 0.011. Okay. That's kind of messy, isn't it? All right. So let's see, I'm going to use these. I think they erase quicker. Kind of smudge a little bit, but save time. Let's see. Yeah, we're on to something different now. Now, that was double displacement reactions in nauseating detail. Now we have acid-base reaction. What's an acid-base reaction? Well, we're going to confine ourselves to this type of acid base, which is a Bronsted-Lowry base. And second semester, we get into much more detail. But for now, an acid is a proton donor. That's an acid. A base is a proton acceptor. Okay. Do you believe that's a proton? As long as we're talking about the this isotope. And you strip away an electron, what do you got left? 1 proton. That's hydrogen. That's why we say proton. Now, deuterium and tritium, of course, they have extra neutrons, and that would fit. But they're minuscule parts. We don't have to worry about that. So that's what I mean when I say proton. And for a strong acid like hydrochloric acid, it is going to completely dissociate into protons and the counter anions like that. Go all the way. That's a strong acid. If you put a base in solution, it's completely soluble. It's going to produce sodium ions and hydroxyl ions. Okay. If you put those two together, those two solutions, you get an acid-base reaction. And what happens is you got, let's just draw it out. You got this. I'm going to leave the aqueous out first on this side. Plus sodium plus hydroxyl yields what? Well, if it's a double displacement, right? This one swaps and takes on that one, and this one takes on that one. So we get sodium chloride in solution, and we get hydrogen and hydroxyls combining to make water. Okay, so the net equation, since this is aqueous, right? Those are spectators. And the net equation for an acid-base reaction is protons plus hydroxyls yield water. That's why it says what it does. Oh, I gotta start this one.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.
Now, what do we mean by neutral? What we mean is that it's not acidic and it's not basic. Right? I learned early on, like grade school, an acid tastes sour, right? Like sucking on a lemon. I didn't learn till later why. The why is those hydrogen ions. That's what causes the sour taste, the response in your tongue. Whereas sodium hydroxide is a base and they taste bitter. Okay, that's why a lot of the drugs that you take taste bitter, because they're slightly basic. And they put them in some sort of capsule or coating so that you don't excite your taste buds with that bitter taste before you get them in your down your gullet. Okay, so these acid-base reactions, what you have to do is decide, do you have an acid? Do you have a base? Right? If you do have an acid and a base, you can approach it two different ways. You can write out the complete equation and do your balancing and stoichiometry with that equation, or you can reduce it. Once you get that, you can reduce it to this one and put in the values here that you may have to derive from your original, and then you can do the calculations using that one. That's usually simpler. But we need some definitions now. Neutralization. Neutralization is essentially saying that when you put stoichiometric amounts of this and this together, you get that and none of that's left. Now, we're going to learn in the second semester that there is a little bit of this and a little bit of that left over. Okay, but it's still neutral. And if you test the acidity using, you ever use pH paper, litmus paper and that type of stuff, the color tells you it's neutral. Right? There's an equal amount of acid-base character and they've neutralized one another. Well, if that's what you're headed for, if that's what you want to do, you can conduct an experiment called a titration. And a titration essentially takes one known, let's, for argument's sake, let's say the acid is a known concentration. And you add base to it, a known volume of the acid, so you know the moles of acid in that container, and you meter out base of an unknown concentration. And when you reach neutrality by a color indicator usually, you know that you've delivered the same number of moles of base as you have acid. And then you can calculate the concentration of your base. That's a titration. That's one type of titration. In fact, titration field is like, it doesn't have to be acid base. It can be lots of different things. But the equality concept is still the same for any titration. When you reach neutrality, in this case, you're at the equivalence point. When you have equivalent amounts of acid and base from this equation, same number of moles of acid and hydroxyls. That's the exact equivalence point. Now, to do it that way in a titration is very tedious because you have to draw a curve and you have to find out where that equivalence point is. So if you got to do 100, 200, 300 in a day, like I and my technician used to do, you want something that can go quicker. And that's when we use a color indicator. It changes colors when you're very close to that point. So close that the error is insignificant. And that's the end point. So the equivalence point is an actual measured, calculated value. The end point is a color indicator that's close to that value. Has everybody heard about phenolphthalein? Phenolphthalein, it's a color indicator. If the solution is acidic, it's clear. If it flips basic, then it'll turn pink. I don't know if you still can, but you used to get phenolphthalein gum or candies, and you give them to a friend or an enemy, it doesn't matter. And they chew on it and it gives them the runs. Okay. So say we're titrating sulfuric acid with sodium hydroxide. Okay. Here's the difference. With sulfuric acid, which is a strong acid, here, and sodium hydroxide in aqueous solution. I think I better remove some of this. If you're doing a titration with this acid and this base, okay, then you're going to swap. You've got two acidic hydrogens here, but only one hydroxyl here. So you're going to end up with sodium sulfate, which is soluble, and you need two of these because sulfate is a 2- charge. Sodium's a 1+. And you're still going to get water. Okay. But that's not balanced because you have two hydrogens here. And let's see. Two sodiums. Oh, two sodiums. Here we go. Two sodiums. You need two sodiums there. That gives you two hydroxyls and two hydrogens, which makes two waters. So you can do your budget and verify, but that's balanced. Okay. Now you know that if you're given 1 liter of 0.5 molar sulfuric acid, 0.5 molar and 1 liter there, we know that we have 0.5 moles of sulfuric acid. Okay. And how many moles of sodium hydroxide are required? Well, if we have 0.5 moles of sulfuric acid, what's the conversion? Sulfuric is in the numerator, so we put it in the denominator here, and sodium hydroxide here. The ratio is 2 to 1. So you actually need a mole of sodium hydroxide to balance that, to neutralize that acid. Okay, that's where stoichiometry is essential. You need to know what the ratio is. Okay. Okay, that's a quick introduction to acid-base reactions. Second semester, we go into much more detail, but that should be enough to get you through titrations that we would do. Let's see, I think we're going to have one. Calorimetry. Yeah, molecular weight of an acid, lab number 6. We'll do a titration then. Redox reactions. Redox stands for oxidation reduction in chemical terms. Right? Anytime electrons are transferred during a reaction, if you've got electron transfer, you have an oxidation reduction reaction. So you could have a precipitation reaction that is also oxidation reduction. You could have a, which would be a double displacement, or you could have a single displacement where you have an element, say, and you have a compound, and then this A just replaces probably the B. So it would be AC plus B. And that would be a redox reaction, and I'll show you why in just a minute. But anytime you transfer electrons, you have a redox reaction. Oxidation is, well, let's give me the acronym. Oil rig. Oxidation is loss. So anything that loses electrons is oxidized. Reduction is gain. So anything that gains electrons is reduced. They always occur together. You can't have one without the other. Those electrons have to go someplace. So if they're leaving this one, they're going to end up at this one. Okay. All right. A perfect example of an oxidation reduction reaction is sodium metal plus chlorine gas to make sodium chloride solid. Okay. This is neutral. This is neutral. This one has a +1 charge and that one has a -1 charge. Right? So that means sodium had to lose an electron, didn't it, to get that plus charge? So what happens is electrons were transferred. Sodium was oxidized, chlorine was reduced. Now it's not balanced because we have 2 chlorines here and we need 2 there, and that means we need 2 here. Now it's balanced. So I think that's what we're trying to show you here in those pictures. It's an extremely violent exothermic, that is, lots of heat reaction. So this one is oxidized and this one is reduced. Okay. Sometimes it's not that simple. So in order to determine whether what is oxidized and what is reduced, we need some rules. The first rule is in your equation, if you have an element off by itself, its oxidation state, we're using that terminology now, the oxidation state is 0, which is equal to its charge, of course. So 1 is elements oxidation state 0. Now they could be standalone like sodium, or they could be diatomic like hydrogen, or they could be quadratomic like phosphorus, or octatomic like sulfur. These are all 0 oxidation states. Okay. Oxidation state of an ion is the charge on the ion. So in this case, that would be the oxidation state is +1 for that sodium ion. Now, some of the oxidation states we have to calculate. So we need to this is an accounting scheme. Sometimes it's equal to the charge, sometimes it's not. Because you can use oxidation states for covalently bound compounds where there's no ion. So this is a bookkeeping scheme, so we can track the electron movement. Oxidation state of oxygen compounds in covalent relationships, oxygen would be a 2-, such as water. If we have water, that's a 2-. That means each one of these would have to be a 1+ to balance the oxidation states. Okay. So, and that's the next one, number 4. But oxygens, if they stand alone like this, but if oxygen is like this, you know what that is? Hydrogen peroxide. You know, that's 3% hydrogen peroxide sitting on your medicine cabinet shelf. Okay. Or in the lab, 30% if I want to do some experiments. But 3% is safe. Now these actually bind the 2 oxygens together and the hydrogens out here like this. So this whole thing is a 2-. So each one is 1-. Whenever you have peroxides, the oxidation state for each oxygen is 1-. Now we go to the hydrogens. When the hydrogen is in a covalent compound, it's a +1, like this one right here. Okay. Fluorine is always -1. Fluorine in any compound is -1. For instance, hydrogen fluoride, -1 +1. The sum of the oxidation states has to be equal to 0 for neutral compounds. For polyatomic ions, the sum of the oxidation states must be the charge on the polyatomic. So if we have ammonium like that, we know that the hydrogen is going to be +1 each, so that's +4 total. But we need to keep one of those pluses out for this charge. That means we only have to balance +3. So this is a -3 for a nitrogen. And it's just adding -3 and a +4, you get a +1. So we added them up and we know that we got the right charge. Let's see, did I miss anything? If I did, I'll bring it up later. I think those are all the rules. Occasionally, you end up with a compound like phosphorus pentachloride. We don't have a rule for that one, right? So you have to assume, since chlorine is in the same group as fluorine, we assign chlorine a -1. That means phosphorus is a +5. Okay. I'm way over already. Let me see. How much more we got to go? We got probably a half a dozen slides to go. I guess everybody's okay with staying, right? Okay, that's fine.
Okay.
No problem. We want to do some examples because this is a skill that needs cultivation. Determining the oxidation states of elements in compounds. This potassium dichromate. You have two options here. If we want to determine the oxidation states, all the alkali, that was left out. All the alkali metals are +1 when they're in ionic compounds. So this is a +1. Oxygen's -2. So if we say 7 times -2, it's -14 total, +2 total. Now, if we put those together, we get a -12. That means that this one has to be a +12 spread between 2. So each one is a +6. Okay, did that go too fast? Okay, the next one is a polyatomic ion. Carbonate. We know our rule says that we can give a -2 to each oxygen, which is a -6 total. But we know that we need 2 of those minuses untouched, unneutralized. So we really only need to neutralize a -4. So a +4 here and a -2 here gives us a 2- total. And you can add them up to prove that I'm right. How about MnO2? Well, it's a -2, -4 total. It's neutral, so that has to be a +4. Let's see. Get the animations in here. There we go. And there we go. And there, that's where we are. Oh, I did PCl5 already. Okay. Now SF4 is easy because we have a rule for fluorine. Fluorine's -1, so a -4 total. Sulfur has to be a +4. That's our bookkeeping scheme. Oxidation reduction, oxidation states. We've already done this one. Except to say that when you lose electrons, you increase the oxidation state. That is, it becomes more positive. Now, it could start off with an oxidation state of -4, and you lose electrons, and you could go up to -1. It's still minus, but you're increasing. You're moving toward the positive. So when you oxidize something, the state increases in value from minus through 0 into positive sometimes. Reduction goes the other way. You decrease the oxidation state when you gain electrons, simply because of the charge balance or the oxidation state balance. All right. Can we determine which one of these is an oxidation reduction and which one is, if any, are not oxidation reduction? The first one is zinc +2 zinc solid +2 HCl aqueous yields, and this should be aqueous to there. And this will evolve hydrogen gas. Okay. We can do the oxidation states here, like 0, +1, -1, 2 plus, -1, and 0. And we can tell that hydrogen went from a +1 to a 0. Right? So we added an electron to get there. It was reduced. So this was reduced. Chlorine didn't change, so it's a spectator. Zinc went from 0 to +2, so it was oxidized by losing 2 electrons for each zinc. Okay, that's the kosher way to do it. The quick and dirty way is if you have an element on one side of the arrow and you find it in a compound on the other side, you have an oxidation reduction. Guaranteed every time. Or if it's in a compound on this side and it's an element on this side, that's an oxidation reduction reaction, without a doubt. B let's see, we do them, yeah, that one. B, if we do the oxidation reductions, oxidation states for each of the elements, we find that nothing changed. Right? I'm trying to save time here. Nothing changed in that reaction. So it's not an oxidation reduction reaction. The last one is a special, actually, I'd want to do this one. 2CuCl aqueous yields CuCl2. Is that aqueous? Yep. And plus Cu. Okay. See, now we know this one is oxidation reduction. Element here in a compound here. This is a special kind of reaction. Notice we only have one reactant here and we get two products. Each of them has copper in it. This one starts off with +1. This one ends up with a 2+, right? Because that's a -1 times 2, that has to balance. And this is a 0. So we've got copper going in two different directions. But notice we got two of them. So one of the coppers is oxidized and the other one is reduced. Okay. This is called a disproportionation reaction. Disproportionation reaction. It's used in the copper industry a lot for purifying copper. Okay. Now, sometimes when you balance these equations, if you've got an oxidation reduction equation, the most efficient way to balance the equation is to balance the movement of electrons first. And then once you've got those electrons balanced, then you go to the atoms and balance them. So we write the unbalanced equation, we determine oxidation states to see if we do have a redox equation. If we do, then we show the electrons gained and the electrons lost using tie lines. I'll show you an example of that. Then we go to the coefficients to balance the electrons, and sometimes that balances the equation. And other times it gives you a more efficient starting point for the budget. So if we have solid zinc in our example here, and we react it with aqueous hydrochloric acid, and that's going to yield, let's see, I think it's 2. I believe that's right. Let me see. What's the unbalanced equation? Oh, okay. We're going to split it into ions. That's fine. Zinc 2+ aqueous plus 2 chloride ions aqueous. There we go. What are the oxidation states on each atom? This one's 0. This one's +1, that's -1. That's a 2+, that's a 1-, and this is 0. So my tie lines would tell me that zinc went from a 0 to a 2+. It was oxidized. It had to lose electrons. All right. So we have a loss of 2 electrons per zinc. And then the hydrogen went from a +1 to a 0. It was reduced. So we have a gain of, went from +1 to 0, a gain of 1 electron per hydrogen. Okay. Let's see, I've got animation in here, I think. Yeah, there we go. Those are your values. And then the tie lines. Now we need to balance the number of electrons that moved. If we say, all right, I want 2 electrons to move this way because 2 electrons move that way. Remember, the electrons must balance. Whenever an oxidation occurs, a reduction occurs by the same magnitude. So we need 2 equals 2 electrons. How do we get that? Well, we've got 2 here for each hydrogen. So we need 2 here. No. Okay. That gives us 2 electrons gained, 2 electrons lost. And that may be the balanced equation. Let's finish it off here. Yep. We don't need any more coefficients to balance the equation. Why? Well, we've got the electrons balanced. Let's tally the rest of them. 1 zinc, 1 zinc. 2 hydrogens, 2 hydrogens. 2 chlorines, 2 chlorines. We're balanced. That was an easy one. Okay. And we're done.